Nice to see many of you so early on Monday morning. And, well, please stop me, ask me. We're chatting, okay? I'm telling you a story and you're asking questions. That's how it works. And I will be correcting bugs as we go along. So first bug is here. Let me just do this. Okay. Right, so, and I will be talking about data analysis, and hardly ever I will mention the word Lisa, because what I will tell you is quite generic and probably it's good or bad, you will decide yourself. Let's start. As I said, I will start with the, well, no, he said. I'll start with the frequentist approach, and it will be rather short, but some things are very useful. Most of the time we're working in Bayesian framework, and that's where we spend most of our time, okay? And I start with the jump directly already to something more advanced. It's what is called match filtering. Match filtering is the technique which is extremely powerful. So if you're searching for the signal of a known shape in a noisy data, especially if a signal is buried in a noise, so it's basically not visible by eye, it's lower in amplitude than variations of the noise, even if noise is have zero mean. And it's used a lot. So, for example, when you're trying to measure, distance, you send a signal, it reflects from some surface, it returns back, and you're looking at time of arrival of the signal, and that's how you're doing, basically correlating of signal which you send with the data, and that's how you measure time of arrival. I will show you how it is done on ground-based detectors with gravitational wave signal, okay? And I will be working both in time and frequency domain. I will be switching between them, mostly in frequency, but sometimes in time. And my noise will be very Gaussian, stationary and Gaussian, until the very end, where I actually will touch a little bit upon what happens when noise is not stationary or not Gaussian. Olaf already introduced you notion of particle density, etc., so I will not spend any more time on this. And I will just demonstrate you what match filtering is. Again, if I'm going too slowly, slow me down. You understood what I want to say? Yes. And otherwise, I will keep going with my pace. And you will suffer. OK, so match filtering. So this is a cartoon. You see the gravitational wave data from Hanford, one of the LIGO detectors. And in black is a real signal, which it's the second gravitational wave signal, so-called Christmas, Boxing Day, it was 26th of December, signal. And my blue is just some kind of cartoon. And so basically, I'm trying to correlate my template, which is basically here, with the data at different instances of time. And on the bottom, you see something what we call signal-to-noise ratio. I will introduce it in the next slide. And I'm looking at the signal-to-noise ratio now. Become a match filtering signal-to-noise ratio as a function of time. And as soon as my signal aligns, or my template, my shape aligns with the signal buried in the noise, I see this burst in the signal-to-noise ratio. And that's how in gravitational wave and ground-based detectors in LISA, it doesn't work very well. It works only for short duration signals. I'll tell you why in a second. But in ground-based detectors, it works very well. It's a very legit technique, and it's used widely to get arrival time of gravitational wave signal. So it works very well if our detectors move. LIGO also does move. So because rotation of the Earth rotates around its own axis, and it goes around the sun. But the signal which we are observing there is no x-axis, but if I put this, it's a fraction of a second. So for short duration signals, short compared to the change in position of the detector, this technique works very well. If times become comparable, it also works, but you need to apply some kind of iterative technique. Anyway, so I told you I will introduce signal-to-noise ratio, and the signal-to-noise ratio will be introduced through these triangular brackets. I don't like triangular brackets. I prefer just normal, these ones. But later on, I will be using a lot of conditional probability, so to distinguish between inner product and conditional probability, I introduce these triangular brackets. And inner product in frequency domain between some time series D and time series H. The easiest one will be to transform them into frequency domain, and then they take this form. This is one-sided parasparticle density. That's why I'm integrating from 0 to only positive frequencies. Again, all of introduce you this quantity. And F max, because nature doesn't like infinities, so in principle everything terminates at some maximum frequency. And this is signal-to-noise ratio as seen in the ideal detector without any noise. However, what I used before in here was what I called match filter SNR. It's a correlation of data with the signal, and I normalize my signal by its norm. All these notions will be clearer once I start to introduce likelihood, etc., etc. So far, just take this basically explanation to this cartoon, what is plotted here, and what is correlation which I compute. Okay. Now, next two slides, basically the most important slides of my lectures, both lectures. If you don't understand that, we should stop talking right now. This cartoon belongs to Michele Vallisneri, and I love it, and I'm showing it with every opportunity I have. What is shown here? So here is simulated data. This simulated data contains two things: noise with zero mean, and the signal buried in it. When previously we were considering match filtering, we assumed that we exactly know the shape of the signal. In reality, these signals have some set of parameters. So for gravitational waves, the signal depends on masses of the, if I'm talking about signal coming from coalescing of compact objects like massive black holes or black holes in general, then it depends on masses of black holes, how fast these black holes spin, what's the distance to the source, etc., position on the sky. And it is generally true that a model of the signals has some kind of parameterized form. And so the signal which is buried here in the noise could have this shape, or that shape. And match filtering and what we do the rest, how we will introduce likelihood, says that if you take the data, if you subtract from data correct signal, what will be left is a noise. And because we assume that our noise is Gaussian, so it means Gaussian noise. So now I subtracted from this data these three shapes, and I get these residuals. So I is a very powerful tool. What is left on the right should look like a pure noise. Which one is correct shape? So if I don't subtract correct shape of the signal, residuals will not look like just noise. It will have residuals of the signal because it's not correct subtraction. So which one of these three looks more like a noise? People showing me. Good. Yes, it is second. It is the middle one. And that is the basic principle of match filtering and basic principle of parameter estimation which we are doing, and basis of likelihood which we will introduce in the next slide. And in frequentist approach, as you see, I did not put exactly blue curve, I put a red one, because you have noise. And in frequentist approach, noise is something which is corrupting your signal. So the whole idea of frequentist approach is that signal and its the parameters of the signal are fully deterministic quantities. But because of the presence of the noise, it corrupts the signal, and the best we can get is the maximum likelihood estimation, well, not best, some estimation of the noise parameters, which fits the data best, okay? And so here, this red curve corresponds to what I will call later, I will explain again, maximum likelihood estimator of parameters. And just to explain again, this theta 2, this corresponds to with the ML. Red one is not actually equal to theta 2 because of the noise. That's the idea of frequentist analysis. And that's the basis of likelihood which we will introduce, which says what I already explained to you. If you take data, if you subtract correct shape of the signal, we should be left with the noise. And since our noise is Gaussian, our probability of residuals having Gaussian noise is basically described by this exponent. So this exponent is not a miracle. It is a property, it's assumption about distribution of our noise. If your noise has different distribution, this will be different function. So, and that's how you build likelihood in most of the data analysis parts, and that's what we use. We almost always assume Gaussian distribution of our noise, and that's why you will see exponent. And the first time, and probably last one, I show you inner product, how it is written in time domain using noise covariance matrix. And now you can transform this into frequency domain, and in frequency domain, this is the inner product which I introduced before. And nice thing about this, it's because in the frequency, you still can hear me, right? It is diagonal, okay? Because here you have big matrices summation, especially if you have a lot of data. Okay, one more important thing. So this is my likelihood, and I will be using this. It's basically tells me about a signal with a given set of parameters. Maximum likelihood would correspond to the best description of the data, given properties of the noise, given the model H and its parameters. And here it's to confuse you even more. I will be using two different notations for likelihood. This curly L and also this one. So to distinguish this, it's a data given parameters, okay? So when you see data given parameters, it means it's a likelihood. This I will be using a few times in the Bayesian approach, just to easier see Bayes equality there, okay? But I will try to stick to curly L as much as possible. If you're feeling lost, stop me, ask me questions. You have this bloody red square, which cube, whatever it is. Okay. So far it's okay? Nothing complicated? Actually, this set of PDF will be yours, so don't worry if you, the most important, you understand what I'm saying. Let's move on. I already said that. Another thing which is, there is a theorem which is basically based on Newman-Pearson lemma, that in Gaussian noise, maximization of the likelihood, this is the best you can do. This is the most, what is called powerful statistics.
Non-Gaussian noise, or?
I will say at the very, very end. Okay. So, for example, if you have different noise model, like, let me give you two examples, okay? I think I will say about, no, there is one student T distribution. It's has Gaussian probability of distribution as a limiting case, but it has heavier tails. So if you think for you that your data has some outliers, which is following non-Gaussian distribution, you might be able to describe it better by student T distribution, and then your likelihood will be based on, basically instead of that formula, we will put student T. There is other examples of distributions which you could use, but here for simplicity, and most of, okay, jumping a bit ahead. There are two types of non-stationarities which you can look at. One is that your C is not stationary, in the meaning that in case of PSD, if you wish, let me go back. This PSD, this one, is basically not only a function of frequency, but it's actually, if you're trying to estimate it for different parts of the data, you see that it's slowly changing. It's basically drift in your noise level. I don't know, Olaf, if you may cover this a little bit or not.
Examples.
Yeah, good. So I don't care. They're just examples. It's the most important for us. And there are second type of non-stationarity or non-Gaussianity which you might have is glitches. And with glitches, you could treat them in a bit different way. You can say that it's actually signals. I just don't know where they came from. You can put the model, some kind of parameterized description of them, and try to model them as the same way as gravitational wave signal. Then you can either treat them as a part of non-stationarities and introduce heavy tails in your distribution, or you're saying, actually, my noise is Gaussian. There is some unknown signals which I'm trying to detect and parameterize and pull it out, and my result still will be Gaussian. Yes, so maximum likelihood, which is basically written here, or likelihood ratio. My likelihood ratio comes usually from frequentist approach, the most common test you can do. You have two models, competing models. First model is just we have noise only. I'll call it M0. And second model, I have data which is described by noise and signal. And if you take a likelihood ratio of these two things, you will end up with this lambda, which is actually log likelihood ratio. Logarithm of likelihood ratios of model 1 to model 0. So I will not come back to this form. If you're writing, maybe you can write it down here, because we will operate a bit with this. Now, there is one more important assumption. I say that my data is S signal plus noise, N, and I use H here. Let me assume that for some parameters theta, actually my model of gravitational wave signal in this case, describes actual true gravitational wave signal coming from the nature exactly. It's not true, and we will discuss it a bit later. One more thing, just to connect, starting connecting dots. If you take this bar, means average over noise realizations. So a lot of things which you're doing in frequentist, you're saying, because you're saying my noise is corrupting my signal, what you're trying to do, you're trying to, in principle, repeat your experiment n times. And then in each experiment, signal will be the same, noise will be different, and you're trying to average over noise realizations. And that's what bar over bar will mean. And if you do, if we can do that, okay, and we'll say what if we cannot, and usually we cannot. And this, if you just do average of log likelihood ratio over different noise realizations, you will see that it's half signal to noise ratio square. So again, a scenario which I introduced before, that's how it's connected to likelihood. So how do we do detection in frequentist approach? I already started saying that you need to repeat your experiment. And you repeat your experiment, if you can, without noise, without signal, so on noise only. If you can kill somehow signal in your data, and you repeat it again and again and again and again. And you, every time you're trying to find maximum likelihood or maximum likelihood ratio, which is basically almost the same. And you build some kind of, let me switch this, distribution of your lambda, okay, that, or likelihood, whatever you prefer. Okay, this is a model 0. It means that there is no signal. And you repeat the same thing for the data where a signal is present. So you're trying to repeat your experiment, and you build another distribution where signal is present. And then, again, you see it's quite, you need to do a lot of searches, basically. You're doing search, if you have big parameter space, every time you repeat experiment, you're doing search. And then what you do, you need to set up your false alarm detection, or for the probability of a false detection. And they call it alpha. So what alpha means, it's alpha is somewhere, so this eta. So it means that this integral, if you integrate over this distribution from eta until plus infinity, it will have alpha equal to alpha. So first you need to build this distribution either analytically, assuming properties of the noise, or empirically by doing simulations and getting the likelihood, maximum likelihood every time. And then you find the threshold. Your threshold, eta, is a function of what you decide to be your false detection probability. So you start with alpha, and that tells you what should be the threshold. And then you're saying, that's my threshold, and everything which I measure above this threshold, I will call detection. It's well-defined and, how to say, procedure. The only thing which is kind of in your hands, but there's something in your hands, is decision-making based on false detection alpha. Of course, if I trying to decrease my alpha, so my threshold will go on the right, and it means to detect or to claim detection, I will need to have stronger and stronger signals, with higher maximum likelihood. As I said, maximum likelihood or likelihood is closely connected to signal-to-noise ratio. Are you with me so far? Please nod so I can see. Okay, good.
Last one question. So when is this frequentist approach used then? Because you said it's not really used, right? You mostly use Bayesian approach.
It is used. I will come back to this when we come to so Bayesian one. I will show examples when people suddenly in Bayesian approach start to remember that there is a frequentist approach, even though it's a mixture and it doesn't make much sense, but people do that nonetheless. There are two cases where it's still useful. Okay, so if you have only one experiment, as we usually do, then you can rely on ergodicity and, for example, that your signals are rare. It means that there could be some periods of time in your experiment which are free of signal, and you assume that there is only noise, and that's how you get the property of likelihood of the just on M0, basically with the noise only, and that's called sometimes background. Okay. In case of ground-based detectors, what is extremely useful, I'll shout for a second. Okay, you have two time series. Okay, coming from two different detectors. And you shift them by time larger than light travel time between two sites. And this means that any coincidence, just by chance, there couldn't be gravitational wave signal, because gravitational wave signal would be within the window of travel time between two detectors. And that's how you could estimate your null hypothesis in case of the ground-based detectors. In case of LISA, it's either impossible or very hard. Okay. So it's, as I said, this thing is quite computationally expensive because you need to build these histograms. Sometimes, in some cases, it is possible to do using assumption of Gaussianity of your noise, and doing. I will show you for F statistic, for example, that it is. With this assumption of Gaussianity, you can get an analytic expression for these two distributions. Right. So once you maximize your likelihood, the parameters which corresponds to your maximum likelihood, it's what's called maximum likelihood estimators. This is what I will call MLE. And I already mentioned to you that in general, maximum likelihood estimator is not equal to true parameters. And the stronger your signal is, the less influence of the noise you have. And the difference between maximum likelihood estimator and true parameters, it roughly goes as 1 over signal-to-noise ratio. Okay, so it's kind of intuitive, right? The larger signal, the small you see the small oscillations on top of it. You can start to see it by eye. And what is another important quantity of maximum likelihood estimator? It's unbiased. It means if you average over noise realizations, then you will get your true parameters. Again, bar means average over noise realizations. So you repeat the same experiment with the same signals, different noises, and you estimate for each time maximum likelihood estimator, and you see that it's on average it goes to this. Of course, it has some variance, and this variance what is called error estimation of the parameters accuracy. It depends on signal-to-noise ratio, and you can get it, for example, using Fisher information matrix. Let me just explain to you a very simple one. So if you have overall amplitude, If your signal could be written as overall constant amplitude plus some time-dependent part, then you can estimate maximum likelihood of this amplitude analytically. I ask you to write down the likelihood lambda, this one. So you just substitute A times H in here, and you take derivative equal to 0, and it's trivial equations. You will find immediately that's your maximum likelihood estimator. If you plug it back in lambda, you will get this expression, and that's your match filtering SNR, square divided by 2. Again, now I'm connecting what I introduced before, like SNR and match filter SNR, to the likelihood, to maximum likelihood, and maximum likelihood maximized over overall amplitude of the signal. Again, a lot of information. Notes will be yours. You can go through this again. You can better absorb, but try to follow my logic so far, okay? Yes, it's also convenient to introduce this normalized template so that h hat is equal to 1. There is one more thing. I'll go quickly because I will never use it before. After that, if you have some initial phase, let's say your signal depends on phase, and you can decompose it initial phase at time equals 0 plus time varying thing. Then you can decompose your signal into cosine and sine of this constant phase 0. And you can also maximize your likelihood analytically. And you will see that your rho max, this match filtering SNR, maximized over initial phase of your signal, is actually given in quadratures, with cosine and sine. There is one big thing. It works for a single voice gravitational wave signal. What do I mean by single voice? It means there is only one, harmonic. If you have multiple harmonics, if you have several voices, so you have addition of several signals with different, let's say, orbital frequencies, then you cannot do that. Or you can do it very approximately. Now, I will consider the case where our signal and our model, H is our model. Our model is approximation to the signal. So it means if I just assuming that let's assume that I know what is S, okay? That in case of two black holes, coalescence of two black holes, my S, for example, would be numerical relativity when they trying to plug Einstein equations into computers, big computers, and simulate motion and gravitational wave signal from two black holes which rotate around each other. And let's assume that this is the best we can do, and it's free of any errors. It's not true. They have their own numerical errors and restrictions and approximations. But let's assume that S is the best knowledge, okay? Of course, I cannot wait for 2 weeks to produce a single model of my gravitational wave signal. I need to do it across full parameter space. So I need to approximate it. Did you already have some waveforms lectures? Good. So let's say my H is EOB or post-Newtonian or whatever it is, or phenomenological. And S is a gravitational wave signal which is coming. So they all have some limitations. We're trying to improve not only speed but also accuracy, but it's hard. Anyway, when S is not equal to H at the true parameters, then it means that our model is approximation. We can try to still get what we like, inner product between true signal and approximation. And we're trying to minimize this difference. Basically, what you see here is distance square. Some kind of inner product is a measure of a distance, right? It is. It is. Okay, so, and I'm trying to minimize distance between my signal and my approximation, my template. And I'm trying to minimize over a full set of parameters. Okay? And I get this theta tilde. That's the one which is minimizing this difference. And I will then do again the same. I will take a difference between true parameters and this parameter which is minimizing the distance between, or difference between approximate and exact model. And I call it delta theta. And that's what is bias in my parameter estimation. It's a nasty thing. Why? Because it does not depend on signal-to-noise ratio. It is the same, it's a property of your approximation. And let me remind you that that's the difference between true and maximum likelihood estimator. Here I'm assuming that S and H are exactly the same. It goes with 1 over SNR. So the stronger signal, the smaller the error. Here, because our model is approximate, it doesn't work like that. And for strong signals, your bias, this thing, starts to dominate. You don't want that. So, and that's why LIGO Virgo, they're more relaxed than LISA people. The signals, I mean, the stronger signal there, it's roughly, you know, I think there was this one on steroids, like 80. And it's already there where LIGO people start to be concerned about biases. The bias is actually comparable or larger than the statistical error because of the noise fluctuations. In LISA, it is really big problem because SNR 80 is a baby signal for emerging massive black holes. Most of the signals which we will observe there, if you see merger, will be hundreds or maybe even thousands. And that's why if you want to make sure that after subtracting the signal that you will end up with a noise, not noise plus residuals because you didn't match your signal very accurately, becomes very important. And for LISA, you want to model your signals very, very well. And yeah, that's a challenge. Can you pass? Yeah.
Thanks.
First time I saw it. Can you do it again?
So is it strictly true that the bias does not depend on SNR, or is that only strictly true in the linear signal approximation, like in the limit of small biases? Is it completely independent of SNR?
I'm trying to think if I have a problem with amplitude only. I think in that case you can be compensated, but it's more to a large extent. But I think it's mostly related to nonlinear parameters. Mm-hmm. I think it will be, those are almost impossible to compensate, especially those which are entering the phase of gravitational wave signal. Right. Because we're most sensitive to the phase of gravitational wave signal than amplitudes. Let me try to draw it. Very simple cosine, okay? If I make a little mistake in amplitude, you see it's basically just that. If I make mistake in the frequency, for example, of the signal, even tiny one, it's very quickly will go completely out of phase. And so amplitude is kind of linear, and most of the time we're not paying so much attention to the accuracy in the amplitude, but a lot of this goes into the phase. And the phase is the most influenced by intrinsic parameters of the binary, like masses, spins, etc. That's why we measure it relatively well. And that's again because we are looking at the shape. We're not looking at intensity like people doing in optical astronomy at amplitude, which is squared. We're looking at the shape. We'll be tracking the phase of our signal. Okay, this is important to difference between what we are doing and what people doing often in optical astronomy. Okay, let's move on. Overlap. There are different ways of comparing signals with approximation or different approximation with each other. One of them is overlap. Overlap, basically, it's a comparison inner product between normalized signals. Basically, you can see this as a unit vectors, and you're measuring the angle between them. This very kind of weird comparison, but nonetheless, it's on mathematical level, it's exactly that. Okay, because you're normalizing your signals, it does not depend anymore on the amplitudes of each of them, but it's looking basically more or less what we just discussed on the difference in phase. And moreover, so basically I'm saying it's between 0 and 1. It's not true. It's between -1 and 1, but -1 it's... let me do this, okay, right. -1. -1 is as good as 1. It's just a signal which is flipped by pi in phase usually. We'll put minus sign in front, and most of our cases we are not that sensitive to the overall sign. Right, another quantity which is often used in the gravitational wave literature, I don't know if it's anywhere else, because faithfulness. Faithfulness is actually a measure of similarity between signal and templates. And it's an overlap between signal. I should not do that. Between signal, S, and your approximation at the true parameters. If it's 1 or close to 1, it means it's perfect. If it's further than 1, it doesn't tell you much besides that it's unfaithful and might have biases. It doesn't tell you how big biases are. Now, if you want to know what biases are, you need to do this. You need to compute what is called fitting factors. So what is fitting factors? Indeed, the model could be unfaithful in the meaning that with true parameters, it does not fit well gravitational wave signal. Nonetheless, you might ask, what if I vary parameters for some other parameters, I'm saying bias, on the expense of the bias? Can I still fit the signal well? And sometimes, and often, answer is yes. My signal, my approximation becomes very close to true signal, but because I am introducing the biases. It's good and bad. It's good for detection. It's good for subtraction of the signals. It means that, if I subtract it, I might get really back my noise. And it's bad because for parameter estimation, it means that what I'm estimating as a parameter is not true parameters, and this could be significant. And the model which allows me to fit well the signal on expense of the bias called effectual, what's called effectualness of the model. To find it, you need to do maximization, let's say, of overlap between signal and the template over all these theta parameters. And that's what's called fitting factors. So fitting factors will tell you two things: if your model is effectual, if it can fit the signal correctly, and maximum theta which you get from here, it's basically the same as the minimum here, will tell you about the bias. Okay. Let's move on. F statistic. So now let's see. Do it. Yeah, cool.
Hi. It was relating to the previous slide here. Faithfulness. I don't see how that's a parameter that we can often compute, because we don't know theta true, right? So unless unless you're comparing one simulation with another simulation, so that means you have access to both the models. Exactly. You have access to the true model as well as the fiducial or the biased model in this case. So that's not a quantity that's quite useful in the live, right, when you're making actual observations, or have I misunderstood something there?
It's not useful when you do observations. It's useful when you're doing waveform modeling.
Okay.
So usually people assume S is a waveform models coming from numerical relativity. There are only a few of them. Well, now it's more and more. Now there are a few thousand gravitational wave signals computed in different parts of parameter space using fully numerical relativity, so solving Einstein equations numerically. And those 2,000 waveforms are used to answer exactly this question. Is my model, like say effective one body or phenomenological template or whatever it is, how close it is in different part of parameter space to what could be true, assuming that numerical relativity gives us a true answer. And of course, the first quantity which they compute is the faithfulness. And they're trying to reduce faithfulness as much as they can. So it is important not for analyzing the data. It's important before you start analyzing the data to model H.
So you choose the best model based on the best faithfulness, but then in the time of production, like when you're making observations, you use equation 7, which is kind of like a match filter, which just tries to find the MLE, essentially, or something along those lines.
Yes. Well, that's exactly what is done in the, I will talk about the searches, actual searches in a few. And there's exactly what is done. And moreover, you can do even searches with the completely unfaithful one, just to find somewhere in that signal, because especially in ground-based detectors, amount of data is huge. Signals are sparse. Now it's becoming like once a week, but still, imagine that you have what sampling rate in the LIGO detectors is 16K, so you still have 16,000 points per second. Of course, most of them useless. You don't sample to 4, but even 4,000 points per second is a huge number. And you can compute how many points you have per day, per week. And out of these points, you have, probably a second or 2 seconds of useful data with gravitational wave signal. So you want to search this data as effective as possible, efficient. And you probably will want to use something completely unfaithful but fast and effectual. Something which allows you to find the signal fast, identify a chunk of data where the signal is, and then follow it up with something more faithful. Still, another is, I don't know if you were here. So, the most faithful currently model is based on numerical relativity. Basically, you interpolate between these 2,000 points. It calls NR surrogate. And at the moment, people think that this is probably the best we can do. And it still doesn't cover full parameter space, and it's very short, because typical duration of numerical relativity simulated data is 2 weeks for ground-based masses. Okay, so it's not very... Sorry, what am I saying? 2 weeks. I'm talking about LISA. 20 cycles, 20 orbital cycles. It's so basically they can simulate roughly something like 20 orbital cycles only. So they're very short. F-statistic. F-statistic, we already looked at this when we maximized our likelihood or likelihood ratio over amplitude or over phases, initial phase. Now, the more generic way, if your signal could be presented in this form, so decomposed in some kind of linear coefficients, back to your question, A, mu, which are not function of time, they're just really coefficients, and the time-dependent part with nonlinear shape parameters theta, kind of curly theta. Then you can plug back this h of t into your likelihood or likelihood ratio, log likelihood ratio, and differentiate it with respect to A. Again, it's a trivial exercise. Log likelihood ratio with this shape of the signal will be quadratic form. You know how to differentiate quadratic forms. And your maximum likelihood evaluation will be given by this. So this M matrix is basically inner product between different subtemplates. X mu is inner product between data and each subtemplate. Okay? And if you plug back this estimation of your amplitude into your H and then H into the log likelihood ratio, you will find that maximum likelihood at the evaluated at the maximum likelihood estimation of these parameters A will be given by this form. That's it. So that is all what you can, I mean, there are literature, papers written on F-statistics, but this is what it boils down to. You compute that, you compute that, you compute this. This is your maximum likelihood. You don't need to care anymore about these parameters. It's nice when you can do it, and often you can do it. I mean, we saw, again, examples, it's initial phase and amplitude. There are more, like in gravitational wave signal case, the A coefficients will also contain inclination, orbital inclination to the line of sight, and they will also contain polarization vector. Sorry, vector, the angle, polarization angle. So 4 parameters. In case of, I think you might see this in tutorials, this A mu, in case of, let's say, galactic binary or something, mildly relativistic gravitational wave signal, your coefficients A mu will depend on amplitude, which is basically distance to the source, initial phase, orbital phase, polarization phase, and inclination. So you will have 4 parameters, A, which will be function of these 4 other real, true, extrinsic, what is called parameters of the gravitational wave signal. Other parameters which entering into here, like masses or basically frequency, it's basically phase evolution parameters. And in case of LISA, sky. Sky enters in two places. It enters into amplitude, and it enters also in the phase as a Doppler modulation of the signal. If you have long-lived signal, that's how in LISA we measure its sky position. Basically, when LISA goes around the sun, signal is over there, source is over there, and it's static. So sometimes you're going toward the source, sometimes away from the source. And your gravitational wave signal becomes blue or red shifted. It enters into your phase, and that's how one of the way allowing you the most sensitive way to get position of the source of the sky. And in this case, you remember what I was saying, you can actually estimate distribution of your null statistic when there is noise only, and it's distributed as a central chi-square with p, whereas p is the number of these parameters. In case of, as I said, galactic binaries, there are 4, so it's a 4 degrees of freedom. Or if signal is present, it's a non-linear, non-central chi-square distribution, and this non-central parameter is a much filtering SNR square. So for this case, you can actually, you don't need to do simulations. You roughly know what should be distribution under a null hypothesis or hypothesis where the signal is present. And you can set threshold based on your false alarm probability and claim detection. This big assumption of Gaussianity of the noise. I already mentioned a little bit about this, that you can also, for transient signals which duration is short compared to the observation time, short compared to the, let's say, characteristic time when position of your detector changes with respect to the source. In ground-based detectors, it's day. In LISA, it's year. So year is, it's, well, of course you don't want to year, but let's say if your signal is 1 day or 2 days in the LISA, and your orbital motion is 1 year, you can actually neglect LISA motion, and you assume it as a static with a high degree of approximation. The same for ground-based detectors. Day is a lot, your signal is less than a second, you can assume that your detector did not move at all during the detection. Okay. In this case, you can construct what's called rho of t. It's SNR as a function of time, and you can effectively, very efficiently compute it using inverse Fourier transform of your inner product. Basically, you're shifting your template along the data over that period of time when you can approximate your detector as not moving. I'm losing you. Look at me, okay? Let's, you know. I know a lot of words, a lot of math. Yes, and one more thing before we go into parameter estimations, more exciting things, is a network. Did you consider A and T, right? And you introduced, so for LISA, you can construct the time series which are kind of almost noise independent, meaning that noise in the one stream does not correlate with, or correlation is very small if you're trying to correlate noise within one and in second. The same in ground-based detectors. You can assume that two LIGO detectors and Virgo, they separated a lot, that the noise of them completely independent and non-correlated. Not entirely true, but to a high extent it is true. In which case you can build what's called inner product. You can extend it to the network, and it basically you sum over the inner products in each detector. What it means that each detector might have different noise power speckle density and different vision of gravitational wave signal. That's what is response. For me, response is included in H. H is what detector sees. It's not what gravitational wave source emits, it's what detector sees, okay? There are two different things between this, and Olaf described to you this. You did. You did. Good. Not a bit, okay, I saw it, you did. Now, I mean, to some extent, we maximized our likelihood over only a few parameters which are kind of constant and boring. The more interesting part is those parameters over which we cannot maximize analytically, and we need to do it numerically. And that's where fun starts. Now, what problems do we face here? The first is the likelihood surface itself. So if you're trying to plot the likelihood surface in 2D and 3D, so basically you have parameter space, and at each point of parameter space you have some kind of embedded surface. Okay? Nature is not so nice, so it's not monomodal. So it means that there is not a single global maximum somewhere there. Usually you meet a lot of little maxima here and there, and they quite often separated by valleys. And so what we want to do is to get a global maximum. Whereas, well, I like this analogy. Usually, it's more applicable to LISA, a bit less to ground-based detectors. You're walking in a forest and trying to find the largest tree. Number of maxima in ground-based detectors significantly lower, smaller, and therefore it's a bit easier. In LISA, it will be, because signals are stronger, it will be harder. So it's the first problem. You're searching, you found something looks like maximum, but actually there is another one a bit further away, which is much larger. And second problem is your parameter space over which you search is big, and size of your maximum, what I call the volume of a template or volume of a signal, is relatively small. And it's like this different analogy. You know, imagine that there is one little hill in a desert, and you need to walk in the desert until you hit this hill. So what do we do? The first, most natural way of dealing with the problem is saying, okay, let me just take parameter space and cover it by net, by grid of points. And then I will compute likelihood at each point of my grid and just see what is the maximum. So this is a cartoon which is showing exactly that. But, so now how do we construct this grid? It's not a grid in coordinate parameters, like mass 1, mass 2. This is the grid in a distance which we introduced, which defined by inner product between two nearby templates. So you take one template here, and you shift it by some small parameters, and that's basically you can do Taylor decomposition. You will have this. This is my old slide, so this is inner product, okay? So this is inner product between derivatives of your signal with respect to parameters. And you can see that this, if you know differential geometry, basically this is the distance and this is the metric. So that defines your metric on the parameter space. Your parameter space might or might not be flat. And that's what this metric tells you. This metric also you might recognize, it's a Fisher information matrix. And if in 2D, this can be represented as some kind of ellipse. If you fix the S to, let's say, 0.01, and you're trying to see all the points which are far away from this by this distance, it will be some kind of ellipse. And that's your two-dimensional parameter space, okay? So that's also what you can see as the size of your signal. This ellipse is the size of your signal. And you want to place these ellipses, in each, and you see the ellipses will change its size in different parts of parameter space and its orientation. I'll tell you what. Even simpler. Try to place evenly distributed points on the sphere. It's very hard. I don't know if it's possible at all. And placing even in flat space-time, not space-time, sorry, in flat parameter space more than 3 dimensions also becomes challenging. Nonetheless, here nature is not too nasty. I mean, if you look at the properties of this metric, it's slowly changing across parameter space. So you can still place templates in relatively well manner. And you can see here, this is what template placement done in the ground-based detectors. You can see they're more dense with small masses and less dense when you're going to higher masses. So it means that it is totally non-flat. It might be even flat, but it might look non-flat in the particular coordinates which you've chosen. Like on this table, it's flat, but I can use Cartesian coordinates or I can use polar coordinates.
Hey.
Cool. Almost.
Okay, so if I understood, the Fisher information matrix here is being used to define a grid that is uniform in this space, right? Like it's well distributed, and you're not wasting your time searching for things that are very similar.
It defines metric. And this metric, of course, could be different based on my parameterization. And again, going back to Cartesian on the surface of the table is constant. The polar coordinates on the surface are not constant. And you probably want not only, even if it's flat, you probably want to choose coordinates which is as close to Cartesian as possible. So computation of the metric does if you want to look at the curvature, saying flat or non-flat, you need to go to quantities like curvature computation. Then what you try to do is basically try to find coordinates theta, describing your model, which make metric as constant as possible. In case of inspiraling two objects, it would be chirp masses, not chirp masses. It's tau. Basically it's coefficients of Taylor expansion, post-Newtonian expansion of the phase, like 0 and 1.5 order. But what I'm saying is that it's important how to not only to compute this, but also to compute to choose the parameters in which you're doing this computation. Let me give you an example here. So parameters here could be chosen such that it is ellipse, or I can make a combination of theta1 and theta2, and it becomes circle. Circle is much easier, much better, so you don't need to align. And probably you want to have circles instead of ellipses. You want to remove correlation from your parameters. So this ellipse means correlation between parameters. It means shift along this direction makes signal vary much faster, whereas shift in this direction makes signal varying much less. Is it clear? Yeah, okay, good. Yes, and here it's also shown where the first gravitational wave signal was detected. It's quite far from the cloud of the points for which we were computing. So, what is good about this method and what is bad? The good, it's very easy to parallelize, so basically you can compute its likelihood in each point, or it's a SNR or whatever you want, at a match filter SNR, at each point completely independently. If you have big clusters, you just simply distribute these points and you compute, and then you reconcile and recombine the results and see what is there. Potentially, because you're covering full parameter space, you will find all maxima, local, global, etc. Moreover, if you have two signals, you could actually see both signals at different parts of parameter space, if signals don't correlate. What is not very good, I already mentioned, is extremely hard to place this uniform grid in a parameter space. There were many papers written on this subject. And computation is very expensive. So it's basically goes, so imagine that you have one-dimensional problem. You can cover it, let's assume you can cover each dimension by 10 points. 1D, 10 points. 2D, 100 points. 3D, you understood in math, right? And so number of computations which you have to do, it goes geometrically. So it's very hard. You can do hierarchical search. You can start with a coarse grid, but reducing possibility that you can have false detection. And you have candidates in parameter space, and then you zoom in that of parameter space, which kind of promising. Another way of overcoming this template placement, it's a dummy method. It's called stochastic method. You take one template anywhere, you throw second one randomly. You compute overlap between them. If it's far away, you accept it. You throw next one, compute overlap with two existing, and you keep throwing until you're tired or until you kind of hit the threshold that after a million trials, I don't see any more holes. There will be holes. And to cover the holes, you can split your parameter space into subspaces. Then there'll be less holes. But then you need to take care of boundaries when you're trying to match different parts. Yeah, that's the way.
This hierarchical search, how does that solve the problem in the forest with the trees thing, wherein you have a tree, then nothing in between, then you got another tree, and then nothing in between, then tree again, nothing. Something like Emery's, like things like that.
The only problem in hierarchical search, which you might see, if it's like a fishing with a net, right? If your net is too big, you will catch only big fish, and you will miss all the small ones. The same here, if your secondary will be, or global maximum is large enough, you will catch it because it will leak in the neighboring points.
Exactly.
If your signal is weak, you will miss it. And that's how you have to deal it. So there is it's a conservation of complexity. You cannot, it's very hard. So this is your design of coarseness of your grid. You need to decide, I don't want to lose SNR's events with SNR, let's say, I don't know, 20. And then it will tell you what could be the coarsest grid you could go with.
Indeed. So sorry, it was the second problem that you had mentioned. The volume of signal is much smaller than the volume of the
that's
search
exactly
volume.
that.
So here, in that case, this still wouldn't solve that because the grid the coarsest grid you can create is still given by the.
Absolutely true, but there is one more word which I said. I will reduce my threshold. I will let leak noise type of signals, okay? So basically, indeed, so the volume, it still has a finite size, okay? There is nothing you can do if it's in the middle of a cell, okay? But however, if you're still near one of the nodes, it will leak a little bit of SNR into the nodes, and by reducing a threshold, you might be able to catch it, because next time you will zoom in and you will find the signal. So it's a trade-off. I mean, it doesn't solve completely. It solves a problem of computational expensive parts. but you need to be smart how to construct the grid size and be ready to lose some weak signals. Now I'm going to something else. How much? Okay, I still have time, right? Stochastic searches, and I will consider only two. They've proven to be probably the most useful. So what do we do here? We're basically borrowing things from the nature. So in the short, basically we do random walk in the parameter space until we hit something which is worth looking at. Okay, if there is some little hill or tree, we basically will walk through the forest until we hit the tree. And we use population approach. So we use, I don't know, like say, I like analog with bees, okay? So we have a hive of the bees, and the bees are flying around, they're searching for maximum likelihood, and then they communicate with each other. How is it done? We have population of bees or whatever, and we evolving them, from one generation to another. And it's in a particle swarm optimization. We have population of these points of particles or bees. We scatter them randomly in the parameter space. It's in your hands how many bees, how many particles you want to have. And then all the bees are flying with constant velocity in certain direction. And then, as the bees start to discover your parameter space, basically they see flowers, so say, oh, it's nice. And it start to, going toward the flower. And that's the first term. This acceleration, it's deviation from your linear motion toward the spot with the kind of little field with the flowers. It's a field of the flowers which are found by a particular bee with index I. And then the bee comes back to the hive and saying, I found this nice spot. And other bee saying, yeah, me too. And they compare information, they have this global best spot. And that's the second part, it's acceleration toward the best global spot. How much this acceleration, each of them play a role, is this coefficient C1, C2, which is also in your hands. And so now bee starts not to fly on the direct line. It has two preferred directions. One is the best spot it found so far, and the best global spot whole hive found over whole past days of flying, okay? And so you evolve them until they basically end up in your global spot. If you have many bees, flying bees, it's good because they discover they're going through different paths to the global spot, and they might see better parameter space. It still does not guarantee that they will find the global maximum. This is the problem of stochastic searches. They will find a solution, but not the solution. You have to live with this. How to deal with this? Make it several times. If they converge to the same time, it gives you more confidence that you found something probably good. Or you make another algorithm, and what is called differential evolution, for example. There you make motion of a bee or a particle based on your partners. So basically, it's a particular case of genetic algorithm. When you evolve, basically you take several parents and you produce a child, generation evolution, and you're trying to improve quality of each generation, and quality means maximum likelihood. So if you prefer points with a higher likelihood. Let me give you an example. So for example, you take 3 points, 3 bees, and you produce another point, another bee, in this case. And then for new generated point, V, you either accept it or not with some probability, what is called crossover probability. Okay? And crossover probability is in your hands, it's between 0 and 1. You can even evolve it also, it doesn't have to be constant. You can adapt it if you wish. And then you select U, if, and substitute with the old one. So for B with index J, you choose U position or your child U, and you kill the parent if it has a higher likelihood. So it's basically a new way of producing new points based on the population's current population. Okay? There are many ways of doing it, a lot of them. This can be seen as a breeding or as a mutation, but basically you propose new points in a parameter space and then either accept or reject it based on your state, on your likelihood. You want to go to the highest likelihood. And again, more particles, more B's you have, the better it behaves. There is always compromise between number of points and efficiency. So you can combine these two methods together. Do you have your code available for people, Sinven? I'm talking to you. Is there somewhere code which does this combination?
Well, so far I know I do it, but okay, people might think that
Anyway, so there will be code which combines these things, and you can try it yourself and see what works. You can, you start with one, then with second, or make each of them. Was it clear, this part?
Yeah.
You said the parameters for these searches are in your hands. In practice, there's probably an optimal set of parameters. That probably depends on the surface you're trying to explore, which you don't know, so you don't know the optimal parameters. But what do you do in practice? How do you choose these parameters?
Yeah. Well, the short answer, try and see what works the best. Okay, there is also some adaptations. There are some codes with adaptation, and they evolve. For example, there is adaptive particle swarm optimization, which evolves these coefficients W, C1, C2, based on the current state of the population. So in the beginning, you want them to explore a lot. And as they converge to some maximum, you want to kind of make it collapsing a little bit. You can have different walkers or different bees. Some bees will be more, so you basically don't do it common, but more, you have subset of the population. Some of them will be much faster converging to the maxima and exploring region around this. Some others will be flying like mad all around, bouncing, and searching for better maxima. But there is important part. You don't want to bee fly to the moon, okay? So you need to introduce boundary conditions. And boundary conditions could be reflective, just bounce it back. Or you can have it, if it's crossing some boundary, you can put likelihood for these points minus infinity, and make it fly, return back on its own, for example. I think it's called transparent.
Is the R1, R2 in PSO have the similar meaning with the R1, R2, R3 in D?
Say again, please.
Is the R1, R2 in PSO?
No, it has different. It's just random variables. It's you randomly draw R1, R2. This is not in your hands. It's just a scaling factor which you go between 0 and 1, which defines how much some randomness in your accelerations. Okay, C1 and C2 are in your hands, and you can evolve it the way you want. What I was describing, might want to have C1, C2 smaller in the beginning and then larger at the end, for example. So at the beginning they're more flying around, and then they slowly start to converge. Because the stronger these terms are, the faster they get to the certain maximum.
Thank you.
And W works like a mass here, basically. Good. We're done with frequentist approach. We're not using it. Thank you. And now we're going to Bayesian approach. And sometimes in Bayesian approach, as I said, we wake up and start using frequentist even though they're not fully compatible. Mm-hmm.
Who's
What do you think about if we use frequentist approach and then we estimate our errors as not the kind of Bayesian errors, but the errors of ensemble? Like if we repeat, let's say, a lot of simulations, and then because we have only one observation, but we repeated that many simulations, and we kind of have, proper error measurement on the parameter. Do you think that would be eligible to do this?
Absolutely. Within frequentist approach, that's what you do. But it's not necessarily will be the same as Bayesian. The main reason is prior. And the prior, that's a good question, so it helps me to switch to Bayesian one. The prior might completely overrule or change the shape of likelihood which you compute.
But practically, most of the time, they're just uniform, right? We don't really use...
It is correct. And still, even in that case, in high SNR limit, they definitely will agree, because they basically start to base mostly on the maximum likelihood, which is ellipsoidal shape, and you can even explain it. You can approximate your likelihood with uniform prior. You can compute what should be the posterior, and in this case, you can show that it's reducing to somewhat Fisher-related kind of type. But in general, especially for when you cannot estimate this with where lowing SNR is not very high, okay, then it's a bit hard to compare these two approaches. But don't underestimate prior. Even if it's uniform, it's still restricting your parameters, whereas in a Fisher could give you error more than 100%. Bayesian will always restrict you to some physical regions within your prior, and they're not equivalent. So now, what's the difference? So I already mentioned the magic word prior, and the biggest difference between frequencies and Bayesian approach is that now signal still could be deterministic. I'm not talking about stochastic gravitational wave signal. I let it leave to stochastic people. But what is important for us is that parameters are not anymore deterministic quantities. They're random variables. And that is the biggest difference. And we will use a lot, you see, Bayes theorem, Bayes equality. And the thing is, because the variables, our parameters are now random variables, we want to estimate distribution of these parameters. And you start with the priors. So before you even start looking at your data, you need to decide on distribution of these parameters. There are several ways. It could be that these parameters coming from another experiment, unrelated. How should I example? I don't know. Some electromagnetic information could give you the prior on the sources. So basically, we know where the source is on the sky. We know that it should give gravitational wave signal. So therefore, we can make very narrow prior on the sky, on the distance, and it's totally cool, nice, and we're doing this. Another possibility is if you have a astrophysical model in your mind, like a galaxy, okay, you know this population when you're trying to model the galaxy, you know distribution of the stars, you know what there should be masses of the white dwarfs and the binaries, for example, the distribution, and you can also take this into account. This will be your prior and totally fine because you did not look at the data yet. You're saying, I assume I like this. I like the model which is coming from Valeria or from Astrid, and I'm just taking it, okay, and I'm using it. And then you start looking at the data. So you set up your, and of course, if you don't know anything, probably the best way is to use uniform or non-informative priors. And there are two types of non-informative priors. First is uniform in it, or it's log uniform. Log uniform is very good because it's scale invariant. So, for example, it's often used for amplitude. It removes your dimensionality completely. There is one more way of choosing priors. It's based on Fisher information matrix. It's called Jeffreys prior. I'm not talking about this. Right. And then you start looking at the data. And data gives you likelihood. And likelihood updates your knowledge on a prior to produce your posterior. That's how the game goes. Take prior, you look at the data, you're picking, okay. And data could be informative on your prior and on your parameters. And then it updates your prior and it becomes, for example, narrower, you're assuming uniform, and then it becomes, picking certain. You started with your box. And then your posterior told you something like this. It means that, it gave you information. It updated your knowledge. Or it could be non-informative, and your posterior is actually equal to your prior or very close. It means that data doesn't know anything about this particular parameter. It also happens. So at the end, what we want to get is these posteriors. Let's look at the formula. And so what goes into this? It's prior. I will always call it pi. It's a probability, so it's basically normalized. Integral of pi over full space is equal to 1, always. Likelihood, something which updates your prior. And here I use p because for you clearly to see basically Bayes equality, okay? Conditional probability. And for that reason, I keep it p for likelihood, and then I will switch back to L. But it is likelihood which we used before. There's nothing different, okay? And that's left-hand side is your posterior. That's what we're trying to estimate. The numerator, it's what is called evidence. Evidence is basically a normalization factor, and you can see this is if you integrate left and right-hand side, it's integral of your likelihood times prior over full parameter space. It is very hard to estimate, and we need it. And where do we need it? Yes, we need it here. So it's very hard to estimate, and most part of my next lecture will be dedicated to how to do that. Let's look a bit more at the Bayes. As you see, yeah. Again, we can put the Bayes theorem, Bayes equality now on the level of the models. Because before, did I do it? No, yes, I did. Well done. I put also model. What is X? Where did you come from? Naughty one, huh? No, it shouldn't be there. It's sneaked in. Right, anyway, let's look now in the level of the models. So when I was doing this, in principle, I also should write here, where is that? Pi of theta I given model I. So I assume somewhat model underneath. So I assume model, for example, of gravitational wave signal is parameterized by thetas, okay? Or I have used a particular model of a galaxy which gives me a distribution of the parameters, okay? And as a result, I always assume there is always assumption about the model which goes into this. And model might not be unique. So here is, again, Bayes equality on the level of the models. And again, probability of having model I, given the data, is equal to likelihood of the model times prior of the model divided by some normalization factor. If you want to ask yourself question, what is the best model to describe the data, you need this quantity. Okay, this probability of the model given the data, given your observations. We cannot compute it because of this. Why? Because what P of D is probability of a data, what it means. It means that you need to consider and basically sum all possible models which could describe this data. And this set is often infinite. Or basically what we're looking at is non-complete set, okay? And therefore we cannot estimate P of D. It's only in a limited number of cases where it's possible. And we can cheat. We can get rid of this constant by doing ratio probability. So basically it's called odds ratio, which kind of saying not in absolute way, but comparative way between two different models. It doesn't tell you that one model, any of these models are good, but at least it will tell you that this model is better than others. But again, it does not answer you if model you're trying is good at all. It might be really rubbish. So odds ratio is actually given, again, I'm using the Bayes equality, a likelihood, so how well data is described by a given model, times priors on each model. And this will be my last slide. This ratio is called Bayes factor, and often is used to make a decision on a model, which model is preferred. The second ratio, give me a second, I'll see you hands, is priors odd, and often or almost always it's assumed to be 1, meaning that I don't have any preference for a particular model. And this is totally wrong when we're doing test of general relativity. We know that the general relativity by far much better than any other theories we have considered. Go ahead.
Within one given model, you also make the choice of a particular parameterization. Is this also how you choose the best parameterization for a given model, or is there like a better way of doing this?
No. So because of this integral, it's actually marginalization over all the parameters. It depends on the prior, and you have to be very careful to choose a prior when you're doing model selection. Because, let me go back here, okay? This your posterior. It's totally inside your prior, but prior could be this, or it could be that. It does not matter for parameter estimation, because your parameter estimation gives you the posterior, which is red. It's always within the prior. But it matters here. So for your model selection, this integral will depend on choice of your prior. Let me explain you why. You're basically exploding your parameter space, your volume of parameter space. And probability of finding the signal or finding false signal much larger when your parameter space you're searching is larger. And therefore, that's what is encoded basically into the Bayes factor and into the evidence, into this quantity. It's saying that volume of your parameter space over which you search matters, because you might have false detection. If signal is weak, then noise might more conspire in some part of parameter space to give you something which looks like a signal. So you see there is a kind of overlap with the frequentist, but it's encoded in a Bayesian approach. I know I'm finishing.
But I mean, just so I understand this correctly, if I, for example, choose a uniform prior with a given set of parameters, and I just take the same model but just scramble the parameters in a nonlinear way, then this other parameterization, if I also choose a uniform prior, will look very different if I relate the two, because the one are not uniform in the other.
So the most important, if you're doing transformation, you do transformation inside this integral, okay? And the integral does not change if you don't change prior. If you saying, I'm going now from uniform in masses to uniform in chirp mass and mass ratio, you changing your priors, and then the result will be different. You're basically considering different astrophysical scenarios, where in one universe is constructed out of the binaries with uniform masses, another with uniform mass ratio, for example. They're not equivalent.
I understand this, but I mean, if I basically don't know the best parameterization, i.e., I don't know in which space I should choose the uniform priors, for example, then it's hard to compare it.
You choose the Jeffreys prior.
That's one of the possibility, or the best is, I would suggest, go to your friends who do some models of, if in case of astro and gravitational waves, it's an astrophysicist who trying to do population study. And they will tell you that most likely you will need to do uniform in masses or uniform in mass ratios. That would be the best. And for example, if you want to talk about distance, use uniform in co-moving distance instead of luminosity distance, which is actually in the amplitude. Otherwise, indeed you can use Jeffreys prior, which is kind of reflects how basically correlations in your parameter space, in some sense. But there is no good advice here. You need to choose your prior. Whatever you choose will reflect in your final results. And that is different with the frequentist one, because the word prior does not even appear there. I'm done here. You're not sleeping yet, but you're close to that, so I think you need to go to have some coffee.
Thank you, Stas. So we reconvene at 10:45, right? And the next Belarus lecture will be Wednesday.
Is it? What time?
10:45.
I don't remember. Okay, let's see.
So yeah, let's reconvene in 10 minutes.
Kanta, how to switch it off?